Welcome back. Look, if you're gearing up for an exam and need to absolutely lock down the highest probability test questions on ecosystem dynamics, you are in the perfect place today. We're bringing you a purely slide-driven, high-yield crash course. We're going to strip away all the fluff and give you exactly what you need to know, visually and directly. So let's get into it.
Here's a quick roadmap for this explainer. First, ecosystems foundational basics. Second, energy flow and productivity. Third, essential biogeochemical cycles. Fourth, ecological stability and succession. And finally, number 5, human impact and rapid revision.
Okay, let's dive right into this. Section 1, Ecosystems, the foundational basics.
I really want you to lock this exact formula in your brain. Ecosystem equals biotic plus abiotic components. It's honestly that simple. An ecosystem is literally just the intersection where living things, your producers, consumers, and decomposers, collide with non-living things, like soil, sunlight, water, and air temperature. If an exam question asks for the fundamental definition, this formula right here is your flawless, full-credit answer.
Now, when it comes to aquatic ecosystems, test makers absolutely love throwing binary contrasts at you. You have got to know the difference between lentic and lotic. Lentic means still, calm water. Think of a pond with lots of algae floating on top. Lotic, on the other hand, means flowing water, like a continuous river or stream, and it's characterized by much higher oxygen levels and organisms that are adapted to moving currents. So remember, lentic is still, lotic is flowing. Burn that distinction into your memory.
Moving right along. Section 2, energy flow and productivity.
Go ahead and take a mental screenshot of this table right now. Trust me, the PR ratio is a highly testable concept. P stands for gross primary production. That's the food produced. R is respiration, the food used. If P is greater than R, the ecosystem is actively storing energy and growing, kind of like a young forest. If P equals R, it's completely stable, like a mature forest. But if P is less than R, that ecosystem is losing energy and dying, which happens a lot due to pollution. This table is basically your ultimate cheat code for understanding ecosystem health.
And this brilliantly illustrates the 10% law of ecological efficiency. Just look at how fast the energy plummets. We start out with plants at 1,000 joules, but the rabbit only gets 100, the fox gets 10, and the apex predator at the top, the lion, gets a mere 1 joule. Why does that happen? Well, it's all thanks to the second law of thermodynamics. Whenever energy is transferred, a massive chunk of it is lost as heat. Mostly because that rabbit and fox are burning it off just running around trying to survive. Ultimately, only about 10% actually makes it up to the next level.
Now, speaking of energy, you absolutely need to know this stark little equation for productivity. NPP equals GPP minus respiration, net primary productivity, which is the actual food remaining and available for the next trophic level to eat, is simply the total food produced, the gross, minus the energy those plants actually use up just to survive, which is respiration. To put it simply, it's gross minus respiration equals net.
So, how do we actually model this flow? Well, the single-channel model draws a straight line from the sun to carnivores, but it completely ignores decomposers. Then you have the Y-shaped model, which splits things into a grazing food chain and a detritus food chain. If a multiple-choice question ever asks you which model is more realistic, always select the Y-shaped model. It includes the decomposers, and decomposers are non-negotiable for a functioning ecosystem.
Shifting gears a bit, Section 3, Essential Biogeochemical Cycles.
So what are they? Biogeochemical cycles are basically defined as the movement of nutrients between living organisms and the environment. See, energy flows through a system and gets lost as heat, but nutrients? Nutrients are the Earth's natural, life-sustaining recycling system. They are used, broken down, and used all over again.
Here are the core cycles you need to be familiar with. There's the hydrological or water cycle, oxygen, nitrogen, carbon, sulfur, and then there is phosphorus. I need you to pay massive attention to the phosphorus cycle. Why? Because exams constantly test this exact piece of trivia. The phosphorus cycle originates from rocks and has absolutely no atmospheric phase, no gases, no air phase at all, just earth and water. Do not forget that one.
Let's zoom back out for Section 4, ecological stability and succession.
A critical definition you've got to know here is homeostasis. It's essentially the ability of an ecosystem to maintain internal balance.
The absolute classic example you should keep in mind is predator-prey populations. They just naturally regulate each other's numbers. If there are way too many prey, predators feast and multiply, which drives the prey numbers back down, which then starves off some predators, bringing everything perfectly back to the middle.
Now pay attention because this naming convention is a classic test trap. Negative feedback sounds bad, right? But in ecology, negative feedback is actually the stabilizing force. It reduces change and maintains that homeostasis we literally just talked about, like the deer and tiger populations balancing out. Positive feedback, on the other hand, increases change, pushing the system way out of control. Think of global warming melting the ice, which then reflects less sunlight, causing even more warming. So remember, negative means stable, positive means spiraling change.
When an ecosystem completely transforms over time, we call it succession. And you are definitely going to be tested on the difference between primary and secondary succession. So the crucial point to remember here is the soil. Primary succession starts where absolutely no soil exists, like on bare volcanic rock, making it an incredibly slow process. Secondary succession, however, starts where a disaster happened, like a forest fire, but the soil is already there. Because the soil exists, it bounces back much, much faster.
Whether it's primary or secondary, succession follows a clear set of steps. It moves from bare land to really tough pioneer species like lichens, then onto grasses, shrubs, trees, and finally arrives at stage 6, the climax community. This is like your mature forest or a stable grassland. It's the final, ultimate stable stage that will basically remain unchanged unless a major disturbance comes along and knocks it down again.
And finally, we've arrived at Section 5, Human Impact and Rapid Revision.
Human activities essentially act as giant variables in these ecological equations, right? On the negative side, things like deforestation, pollution, and climate change can push ecosystems way beyond their carrying capacity, leading to biodiversity loss. But on the positive side, human interventions like afforestation, which is planting new forests, along with conservation, recycling, and renewable energy, can actively help restore an ecosystem's resilience and its overall ability to recover.
All right, pencils ready, minds focused. Let's rapid fire this revision. Ecosystem, living plus non-living. The sun, that's your ultimate energy source. Energy flow, one single direction. How much energy actually transfers up the food chain? Exactly 10%. The productivity equation, NPP equals GPP minus respiration. Boom.
Let's keep that momentum going. Lentic waters, still. Lotic waters, flowing. Primary succession, no soil. Secondary succession, soil is already there. The final stage of an ecosystem, the climax community. And what's the internal balance that keeps nature running smoothly? Homeostasis. Seriously, lock these binary definitions into your associative memory right now, and you will absolutely dominate those multiple choice questions. I want to leave you with one final thought to chew on today. As human activities continually test the absolute limits of ecological resilience, can our positive impacts, our conservation efforts and renewable energies, ever truly create a brand new global homeostasis? Or are our negative impacts driving the entire planet toward a permanent climax community shift? Think about how the definitions we just learned apply to the real world right outside your window. Good luck on your exams and keep learning.